now we're going to make our equations non-dimensional. So here are the Navier-Stokes equations for fluid mechanics, which hopefully you're now really starting to recognize. We have the continuity equation, that is conservation of mass for 2 dimensions in compressible flow. We have the x momentum equation, and we have the y momentum equation. So those are your 3 governing equations. And we're going to make these non-dimensional. And the way we do that is we identify an appropriate scale for the problem. So you can choose different scales for the problem. We're going to choose a length scale, and we're going to choose a velocity scale. So we select usually just one. You can select 2 length scales in certain circumstances, but we're going to select a length scale, and I'm going to call it L here, but it doesn't have to be L. It can be any length that is characteristic of the problem. So if it were flow around a sphere, you wouldn't choose L, you would choose D if that was what was going on. If it was flow in a duct, you might choose, the hydraulic diameter of the duct or some dimension of the duct that makes some sense. But we're going to call it L right now. It's a length scale, any length scale that's appropriate for the problem. And similarly, we're going to also choose a velocity scale. Again, I'm going to call that scale right now U infinity, but it doesn't have to be some free stream velocity. It could be any velocity that appears something you could know in the flow. And it seems like it's typical of the velocity scales in that flow. So if it is flow over a plate, then obviously U infinity, the atmospheric flow velocity, would make a lot of sense, or flow around a sphere, then the U infinity free stream velocity would make sense. If it's flow inside a duct, maybe some other velocity might make more sense, like the mean velocity. So we'll see how you choose those later. But the point right now is it doesn't matter what we choose. We have one length scale and one velocity scale, and that's going to allow us to non-dimensionalize this problem. So we got to define some dimensionless variables. So these variables do not have dimension in them. So this is the symbol I'm going to use for dimensionless, this little tilde. And then it's going to be U, the actual velocity, which has units of meters per second, divided by the characteristic velocity that I'm chosen. So I'm going to have a velocity divided by a velocity. So that's going to be meters per second over meters per second. So that's going to have no units at all. Similarly, I'm going to have a dimensionless v velocity, and I'm going to use the same scale here. So I'm going to use the characteristic velocity, whatever I happen to choose. As I say, it could be U infinity, but it could be some v velocity. Doesn't matter. But I'm going to use the same one for both. So they both have the same characteristic velocity in the denominator. That makes this term also dimensionless. Finally, I'm going to choose my length scales then. So my dimensionless length is x over L, and my y is going to be y over L. So those are my 2 dimensionless length scales. So this is going to go from 0 at x equals 0 to 1 at x equals L. This is going to go at 0 at y equals 0 and 1 when y equals L. So they're just going to be scaled the same way in this particular example. Sometimes people choose to make this y over h, then you end up with 2 different length scales in the problem. That can be useful in certain circumstances, but we're just going to keep it simple since we're not looking at any particular problem yet. We're just looking at problems in general. So now what we want to do is use these and substitute them in to these equations. Well, we don't have v tilde, so we can't substitute that, and we need to solve this for, this should be a v, obviously. So, sorry, v over u infinity. So v over u infinity there, sorry. So that's v tilde is v over u infinity. So we need to substitute in for v. So I need to solve this for v. So v is equal to v tilde times u infinity. So that's what I can substitute in wherever I have a v. So I'm going to go up here, put it in all these places. Oh, that's a new. All these places where I have v's, I'm going to put in this v tilde u infinity. Similarly, I'm going to put in everywhere I have a u, I'm going to put in u tilde u infinity. All right, so every single one. This, I will point out, this u infinity, that's a constant, because we just picked a particular velocity for the problem. So that is a constant, but this is a variable. So this matters because we want to put these things into derivatives. And if it's in a derivative, then if it's a constant, I can pull it out. And if it's not a constant, I cannot. Similarly, my x here is going to be L times x tilde, and my y is going to be y, L times y tilde. So those are all my scales that I'm going to start plugging into my equations. So So I'll start with the conservation of mass. So du dx plus dv dy is equal to 0. And I'm going to plug in my scales, which are here. So my v is equal to v tilde times u infinity. And my u is u tilde times u infinity. So I have d of u tilde u infinity by dx. Well, x is L times x tilde plus dv dy. So v is v tilde u infinity, and y is L y tilde. And that's supposed to equal 0. That's what the conservation of mass says. So what do I do with this? Well, I can pull out constants. So I'm going to pull out u infinity, I'm going to pull out L, pull out u infinity, pull out L. So I have u infinity over L times du tilde dx tilde plus u infinity over L again times dv tilde over dy tilde is equal to 0. So far, so good. Now I can simply divide by u infinity over L both sides. 0 divided by that is still 0. And I end up with an equation that looks basically unchanged. So I can see that some of you might be thinking, well, there was a lot of work to achieve nothing. We have the exact same equation we started with, and that is true. It's not true that it's for nothing, however. We will see that while this equation becomes basically identical, not all the equations will become identical. They will have slightly different forms depending on whether they're dimensional or not. But anyway, that's our first one. So du dx dv dy is equal to 0 in dimensionless terms. No real change there. All right, let's move on and take on a tougher equation. So we'll go ahead and do the x momentum equation. Du dt plus u du dx plus v du dy equals minus 1 over rho dp dx plus nu d squared u dx squared plus d squared u dy squared. There's my x momentum equation, and I'm going to do the same thing. So again, I'm plugging in for u. I'm going to plug in u tilde L. For v, I'm going to plug in v tilde L. For x, I plug in, well, I just did that with u tilde u infinity, u v tilde u infinity. For x, I plug in x tilde L. For y, I plug in y tilde L. So those are our scales, right? U infinity, v infinity. All right, so we plug those in. So I get d by dt. Actually, I think I'll move to another piece of paper so we can continue down the page. D by dt of u tilde u infinity. U tilde u infinity d by dxl plus v tilde u infinity d u tilde u infinity d y tilde l rho dp dx tilde l plus nu d squared u tilde u infinity dx tilde l squared d squared u tilde u infinity d y l squared. Okay, so that's we've plugged all of our u infinities and xl's and yL's in. I think we did right. There's a u, x, u, y, v. That looks good. So all looks okay to me. So we'll try to pull all our constants out here. So we've got u infinity times du tilde dt plus u infinity squared over L times u tilde du tilde dx tilde plus, again, u infinity squared over L, v tilde du tilde dy tilde is equal to minus 1 over rho dp over dx tilde with a 1 over L in front. So I move that L out here. So minus 1 over L rho. And then plus nu, and I can pull out u infinity over L squared. And then I have d squared u tilde dx squared tilde squared and d squared u tilde squared, I'm sorry, dy tilde squared. All right, so that's everything pulled out. All the constants have been pulled out, and that's what we think it looks like. Double check to make sure it's didn't make any silly mistakes, but I think it looks okay. So now what I want to do is make some of these terms truly dimensionless, so they have no dimension. So what I'm going to do is I'm going to get rid of u infinity over L, u infinity squared over L. Here I'm going to divide by that, and that'll make this term have only dimensionless terms in it. So I'm going to divide everything by u infinity squared over L. So that's going to give me out in this term when I divide by, so I have u infinity divided by u infinity squared over L, and I have du dt. And then the next term has nothing in front of it because that's what I'm dividing by, du dx. And the second term also has u infinity squared over L, so that's also going to have nothing in front of it, du dy. The third term is my pressure term, so I had minus 1 over L rho, and now I'm dividing by u infinity squared and L on top. And so that gives me dp and dx tilde here still. Haven't done anything with p yet. And then I have my new terms, my viscosity terms, where I have nu u infinity over L squared, but now I'm dividing by u infinity squared over L. And that's going to be d squared u tilde dx squared tilde plus d squared u tilde dy tilde squared. All right, so that's that. And obviously some things cancel. So I've got this going to cancel that, u infinity. I've got L's canceling here. And I've got L's canceling here and u infinity canceling there. So it's going to clean up a bit. See what that looks like. So I have L over u infinity du tilde dt plus u tilde du tilde dx tilde plus v tilde du tilde dy tilde equals minus, what's left on this? 1 over rho u infinity squared times dp dx tilde. And then plus, I have nu u infinity and 1L. And then I have d squared u tilde dx squared plus d squared u tilde dy squared. All right. Notice that, at this point, some things are starting to pop for me. This, you can look at that. Hopefully you guys are starting to recognize that. That's going to be something you know. This is looking interesting. Notice we haven't done anything with pressure yet, but this is rho u infinity squared. That's a lot like dynamic pressure. So we're going to use that to make that dimensionless. Haven't done anything with time yet, and we'll take care of time over here in the next lecture.